Testing. You're on.
All right. Welcome, everybody. Thank you for joining our second day of the NICSITE annual meeting. This session is focused on evolving intersections. So hopefully you found the right session. My name is Kevin Bauman. I work with Kimley Horn, and I'm also the NICSITE Signal System Users Group Chair. So definitely excited to be here with everybody today. Before we dive into our presentations, I want to thank our session sponsor, which is Stantec. So thank you, Stantec, for your continued support of NICSITE. I'm gonna hop right in and introduce our first presentation of the day, which is going to be focused on multi-lane roundabouts. So let me do a quick intro of our presenters, starting with Dr. Zachary Bugg. Zach is a senior engineer at Kittelson and Associates in Wilmington. In addition to project work in transportation planning and operations, he has led or contributed to over 60 single and multi-lane roundabout design peer reviews and feasibility studies in North America, including 36 in North Carolina. And he's instructed over a dozen professional workshops on roundabout design and operations. Zach is a member of the TRB Standing Committee on Performance Effects of Geometric Design and co-author of NCHRP Report 772, Evaluating the Performance of Corridors with Roundabouts. Our second presenter in this group is Justin Bansen. Justin is a principal engineer with Kittelson and Associates based out of Charlotte. Justin served as the primary author for developing NCHRP Report 672, Roundabouts, an informational guide, second edition. And he's currently serving as principal investigator for a Federal Highway Administration pooled fund study to develop countermeasures for reducing exit crashes at multi-lane roundabouts. He has played an integral role in over 250 roundabout projects across the country, conducting peer reviews, preparing feasibility studies and concept designs, and supporting final design and implementation and conducting reviews of in-service roundabouts. And last but not least, we've got Jim Dunlop, who has a bachelor's degree in engineering from Duke University and is a registered professional engineer. He has been employed by the Transportation Mobility and Safety Division of NCDOT for over 30 years, first in the signals and geometric section, including 7 years as systems engineer, and the last 21 plus years as head of congestion management section. Previously, he spent 4 years at the town of Carborough as the town's transportation planner. So that's a quick intro for our first group, and let me turn it over to Zach, Justin, and Jim.
All right, Zach, you're gonna pop up the screen. And I will kick off. I'm taking credit for Zach and Justin's work. And they allowed me to introduce them and their topics. So thank you, Kevin, for those introductions. Our presentation today is about emerging trends for multi-lane roundabouts. As an overview, I'll talk a little bit about status of roundabouts in North Carolina. Zach will talk about research and evolving practices for pedestrians at multi-lane roundabouts. And then Justin will talk about research on key multi-lane roundabout crash trends. And now just a quick bit bragging about roundabouts in North Carolina. Much of what I showed during my NICSITE Back to Basics presentation in May, but I have some updated statistics. Kittelson maintains an inventory database. If you haven't gone there, it's a great tool. You can browse around, see what every state is doing. From this slide, you can see we're third in the country, just a little bit behind Wisconsin. Hopefully, I hope to catch up soon as we can get some of our 150 or so roundabouts currently in design on the ground. And then on the next slide, you can see a summary of our roundabouts here. This is in the inventory database that I maintain for the state. I have 455 roundabouts identified with 43 partial or full multi-lane roundabouts. The map in my inventory spreadsheet don't quite line up right now. Working to fix that. I also keep track of roundabouts near schools since that's a frequent comment or concern. On the next slide, here's a map of the locations. You can get the link when you download the presentation. They're showed by jurisdiction on state municipal roads, a few on private property, including universities, and 2 on military bases. If you know of one that's not on this map, send me the link. Send me a Google link to the location. I'll take a look and see whether it fits under roundabouts or circles. On the summary page, on the summary page, I included a list of roundabouts at freeway ramps, which is also a filter on the Kittelson inventory. This emerging trend in the state. If you're working on a new or renovated interchange with relatively low volume, roundabouts at the ramp intersection should be your default. This improves safety, especially concerning wrong-way drivers, and should last for decades without changes. Now, finally, to the primary subject of this presentation on the next slide, multi-lane roundabouts. We have about 40, with most of them being 2-1, with 2 lanes on the through street, on the main street, single lanes on the side streets, although some of them may have right turn lanes. I'll specifically point out the series of orange dots in the Rocky Mount, where we've let a design build contract to widen Eastern and Sunset Avenues with a new interchange at 95. There'll be 7 multi-lane roundabouts on the corridor, including the ramps. If you're building a new corridor, why automatically install poorly working traffic signals when you can have a great operating corridor such as this one once it's completed? As I've said, when in doubt, roundabout. So now I'll hand it over to Zach talking about pedestrian research.
Thanks, Jim. So there's a lot of new trends in roundabout design. I want to focus on one of those trends. We're still working on multi-lane roundabouts, and it's an evolving practice. Single lane roundabouts, I think most of the research has been going on for the last 30, 40 years. And really multi-lane is where we're still kind of working through a few issues. So pedestrian accessibility is what I'm going to focus on today. There's plenty of other evolving trends in design for multi-lane roundabouts. Roundabouts are good for pedestrians. I think we've established that. Most of the benefits occur, again, to pedestrians because of the lower vehicle speeds, the shortened and lower decision points for drivers, the separated and reduced conflict points. Unfortunately, they still present challenges for visually impaired pedestrians. And so you got an example here. Think through what a crossing environment is like for a blind person at a signal or at another type of intersection. There's typically an audible signal or something like that, where the pedestrian has more clues that the crosswalk is there and that vehicles have stopped. At a multi-lane roundabout, traffic is always moving. It's difficult to hear those audible cues. And so really we're thinking through identifying where the crosswalk is, identifying when our driver is yielding, and then being able to find your way across the crosswalk and complete the journey. So going to the next slide, here's the research, here's the design practices that we've always known about for roundabouts. Most of these are described in NCHRP report 672. These still hold for multi-lane roundabouts, but what the research has shown is that really you need some additional treatments to make multi-lane crosswalks accessible. So I've got an example here from Cramerton near schools, near a school complex. So this kind of shows you all the different treatments described on this slide. Yeah, I'll go to the next slide and just kind of talk through some of the additional treatments that may be needed at multi-lane roundabouts. So this research report 834 from NCHRP and TRB, that includes a very quantitative multi-lane roundabout and channelized turn lane crossing and wayfinding assessments. It really takes you through those 4 steps of locating and the crosswalk and determining when it's safe to cross the street. Ongoing rulemaking by the U.S. Access Board. This has been going on and planned for the last 10 years or so, but really the requirements that will be enacted eventually, they state that some signalized form of crosswalk or an equivalent treatment is going to be recommended at all multi-lane roundabout crossings. And so just having those tools in our toolbox from 672 and some of the previous research for roundabouts is not going to be enough. We're actually going to need to add some additional treatments. So I'll provide some examples on the next slide of what these are. Many of you know an RFB, so the rectangular rapid flashing beacon. Here's an example from Davidson, right on the main drag here between I-77 and Davidson College, of what that looks like at a roundabout. The pedestrian pushes the button and the strobe effect signal comes on to provide really that additional indication to the approaching driver that someone is about to cross or is in the crosswalk. Here's an example from Florida in the lower right with an overhead installation of the RFB. And then another type of solution would be the raised crosswalk, which showing an example here from a 3-lane roundabout in Austin, Texas in the lower left. Really that raised crosswalk has been really proven to help drivers yield, or to really enforce the yielding of drivers to pedestrians crossing at the roundabout. A couple of other treatments on the next slide here. The hawk signal, also known as the pedestrian hybrid beacon, it allows you to have that regulatory requirement, so the full red signal and the wig-wag flashing red. I won't go through the whole operation here of a Ph.D, but this is something else that would be considered an equivalent signalized treatment at a roundabout. And then I'll go through some crosswalk placement techniques, but here the lower right is so the staggered crosswalk being one of them. You're able to independently design the entry and exit crosswalk and how you place that upstream or downstream of the yield line. So what does that mean, and why would we look at placing the crosswalk farther away from the yield line? You know, typically the guidance has said try to go for a 1 to 2 vehicle distance upstream of the roundabout. We may consider lengthening that, especially when there is a signalized treatment, so you can provide conduit out there, provide adequate spacing, especially on the exits, so that a driver or a vehicle can see that overhead signal installation and have a space to actually stop, having that stop bar about 40 feet ahead of that signal. And then also for queue storage, if you've got higher vehicle volume, you may want to be able to provide that additional queue storage on the exit so that there's not as much queue spill back into the roundabout. Then finally, having the visibility and the reaction time and the braking time for vehicles going to that exit, traveling through the roundabout, and then having the distance to brake ahead of the exit. So really what this all comes down to is if you look at the way these crosswalks are designed, they weren't tacked on to the very end of the design, at the 95 or 80% level. It's really critical when you're designing a multi-lane roundabout to think through the pedestrian accessibility implications and what treatments you're going to have out there early in the design, so you can start designing those splitter islands and those approach legs appropriately, instead of just kind of waiting till the end of the design process. So we're going to switch gears here and go to Justin's part of the presentation to talk about the FHWA pooled fund study.
Thanks, Zach. So FHWA sponsored an ongoing pooled fund study that's focused on crashes at the exits of multi-lane roundabouts. I think most folks are aware that roundabouts have been identified by FHWA as a proven safety countermeasure. CMFs and SPFs and other safety research that's been done over the past 20 years has consistently shown that roundabouts provide an excellent safety benefit for in reducing crashes at intersections, particularly with reducing severe injury and fatal crashes. However, there's been some trends at 2x2 roundabouts specifically, so these larger multi-lane configurations, where we're seeing patterns of crashes appearing near the roundabout exits. It's not all roundabouts, but it's been enough that FHWA really wanted to get a handle on what might be these root causes and contributing factors for why some 2-lane roundabouts are operating great and why we're seeing higher numbers of PTOE crashes appearing at some of these other roundabouts that are in the field today, and then identifying some countermeasures and maybe some guidance for practitioners to help try to minimize those situations from occurring in the future. The project team for the study is Virginia Tech, Kittelson, and Quality Counts. We just recently finished field data collection and are currently analyzing data So we're not going to be presenting results today, but really my goal was to try to bring awareness of the ongoing study and share with you some of the key crash types that we're seeing at some of these multi-lane roundabouts so that you can be aware of it going into any designs that you might be working on. So the first crash type we're going to talk about is some of these geometric influenced crash types. And when we get into 2x2 roundabout configurations, especially, the geometry can play a pretty big role. There's lots of variations in lane configurations and size and shapes and alignments, but some of those can have a direct influence on conflicts. And this is an example that's taken out of NCHRP 672. So if you're interested in going in and exploring this one further, I'd encourage you to go in and look this up in that document. But basically the skew between the legs of the roundabout is creating a separation between an entry and an adjacent exit. And so even though the lane configurations are set up where there should be no conflicts, that merging that occurs between those legs results in the potential for a crash at a downstream exit. The same thing can happen when we get diameters that are too large. We started getting away from rotaries in the US and those very large diameter circular intersections because of some of the weaving that occurred and because of some of the crash issues that were occurring. But even if we get at the upper end of the typical range for modern roundabouts, say getting closer to that 300-foot diameter range, we're starting to see some of those same trends appearing. So in this particular example, you're seeing a diameter that's about 300 feet, and you're seeing some separation between that entry and the adjacent exit. And that allows for situations where cars might try to merge next to each other. And then as they get to that downstream exit, there's a crash that can occur. This particular site was a high crash location. And this example that's shown here on the screen was a very common crash trend that was occurring at this particular location. Another one is improper left turn conflicts. And this can also be influenced by geometry. In the series of images at the top, the same roundabout, because of its size, if you look at that top middle image, just about before the drivers get to the roundabout exit, you can see that the driver in the outside lane, their path is sort of aimed and aligned where a driver might think that they can continue to circulate around. They're already in that curved path where they're being aimed around the rest of the circulatory roadway. And so drivers naturally were taking that path. Whereas if you provide some tangent, if you help channelize drivers more towards the exits, reducing the potential for some of that to happen. But as you can see on the bottom of the screen, it doesn't prevent it entirely. There's an example where you have more tangent, you're aligning drivers more to the exit, but you're still seeing some of those crashes occurring. So it's not a matter of relying on just the exit geometry, but it's really a matter of, is the signing, is the guidance that we're giving to drivers upstream of the roundabout, getting them into the correct lane before they get into the intersection. And then there's also a component that we're finding that's directly related to origin and destination. The downstream destination of drivers where they're setting themselves up to go to a freeway on-ramp or a business or something like that is also influencing some of these cases where drivers may be selecting the improper lane to be utilizing. So how can we address that through either the design of the roundabout and the lane configurations we're setting up, or through the signing and markings to make sure that we're getting them into the proper lane. Another common crash type, and we've already kind of alluded to this previously, so in the previous slides, is a situation where you have a driver in the outside entering lane failing to yield to drivers in the inside circulating lane. So drivers see that outside lane open, and especially in situations where you have a heavy left turn in the circulatory roadway, a driver may presume, the driver at the entry may presume that the circulating vehicle is going to be making a left and continue to circulate. They'll try and pull in adjacent to that vehicle. And if the vehicle is exiting in front of them, instead of making a left turn, there's a crash that can occur. And so we've clipped a couple of examples of that we pulled from some of the drone video that we collected to illustrate that, that crash type that's been happening pretty frequently. Other examples that we're seeing are right turns from the incorrect lane. So people making a right turn from the left lane. We're seeing this, it's actually been more prevalent than I was expecting getting into the field data collection and analysis. We're tending to see it a lot where there's heavy lane imbalances. So in this case, you're seeing a queue built up in the right turn lane, and then you have the left turn lane open. And so drivers are coming up to the yield line and attempting to make that incorrect lane because they're seeing this free lane available. And then also we're seeing challenges with exclusive lanes. So where you've got, in this particular case on the right side, you've got a dedicated left turn lane, and making sure people are getting into the correct lane before entry. Again, in this particular case, we were seeing drivers getting into the incorrect lane, realizing that once they were within the roundabout, and then trying to make that late lane change to go to their intended exit. And all these are really a result of some of the additional complexity we get into from these 2x2 configurations. You tend to not see a lot of these in the simpler 2x1 configurations, which are actually more prevalent. But there's a lot of factors that go into this. And I think part of the confusion for drivers is that there's so many different variations of size, position, approach alignment, entry and exit geometry, different lane configurations, different spiral designs that they may encounter. But there's no two that are quite alike. So that's what we're trying to distill down is, are there some common themes that we can be able to help, maybe not standardize roundabouts, you're never gonna have a template, but try to evolve some of the design practices a little bit more. Note that on the two images here, they have slightly different spiral designs, whereas in the top image, you've got a painted spiral, and what ends up happening is the drivers are following the edge of the central island, and they may find themselves, when they're making a left turn, getting trapped into a left turn lane, and then trying to then make a late lane change to exit. Versus the lower image, you actually have the spiral built into the apron of the central island, into the truck apron. And you can see in the image that it's forcing drivers into that outside lane a little bit more effectively. You can actually see the oil stripe on the pavement on the pavement that that drivers are tending to follow that intended path and pushing to the outside lane. So some subtle details like that really seem to be making a pretty big difference in terms of how drivers are navigating these multi-lane roundabouts. Signing's another big area where there's a lot of variation throughout the US. You've got variations in lane use control signing with some side-mounted signing, some overhead. We're seeing examples of successful safety performance, and we're seeing examples of crash problems with either case. So it's not necessarily one is automatically better than the other. It's kind of the whole package coming together. But situations like in that upper corner or the upper image where you've got relatively small lane use control signing, and then it's set back an extra 12 or 15 feet away from the travel lane, in this case due to an auxiliary right turn lane, that starts to maybe impact the driver's ability to be able to effectively see and understand that signage. And so in those cases, maybe larger signing or going overhead becomes part of the consideration. The guide signing and getting people into the correct lane, especially where there's interstates or other routes, also can be a pretty big factor, especially when you're considering some of those OD influences. Markings are another element where there's some variation. Some states are very strongly utilizing what's currently in the MTCD with a solid lane line and dotted lane line combination that's in the upper image versus a strong dotted line that's in the lower image. Again, both are, there's examples of roundabouts that are performing great with both alternatives. There's examples where we're seeing high crashes with both. So the line type and the sign type aren't automatically dictating the safety performance. But again, it's that whole package that's coming together that seems to be having the biggest influence. Similarly with arrows, there's variation in standard arrows versus hook arrows. I will say that kind of anecdotally, it seems there's a trend as people are upgrading some of the roundabouts or addressing some of these crash problems, doing some retrofits, that they're tending towards the standard arrows more so than the hook arrows. But again, that's very region by region, state by state in terms of preferences and what drivers are used to. As part of the study, we've been collecting drone data at 9 sites in Indiana, Ohio, New York, Florida, and Wisconsin. So at each site, we're collecting 8 hours of tethered drone data, and then taking that back to the office to do some additional analysis, both on crashes as well as on conflicts. So we're looking at some lane by lane volume reduction to be able to look at the specific lane each driver used to make their turn maneuver. And then we're also breaking that down kind of minute by minute to be able to look at whether there was some cues forming during those time slices and be able to look at some of these lane imbalance issues that might be popping up. But then we're also looking at logging of conflicts and violations, looking at near misses, looking at potential conflicts, and looking at just violations and time stamping those where we can compare them against some of the volume levels to start looking at trends. Out of the 8 sites, 3 of them are comparison sites that are sites that are performing well, and the rest are sites that are kind of problem sites that are experiencing high numbers of crashes. So we're trying to see if there's any type of lessons we can learn between the two in terms of how these conflicts and violations are playing out. I'll give you a quick example of one of the sites that we're looking at. It's in Carmel, Indiana. We've got 2 sites that are separated about a mile apart. One's at 106th and one's at 116th. We've got both sites are 2x2 configurations. Both are adjacent to an interchange. Both are adjacent to a hospital. Both are adjacent to other roundabouts. So pretty similar. Carmel, for those that don't know, has close to 100 roundabouts now. It's one of the top cities in the country in terms of number that have been implemented. So this is a familiar driver population, and these are close enough together that the drivers, we shouldn't have a big difference in terms of the types of drivers that are navigating these on a daily basis. And yet we're seeing a pretty big difference in their safety performance. Real quick, just in terms of the geometry, both are similar sizes. The biggest difference from geometry perspective is that the one in the lower corner or right corner has one approach that's got an exclusive left and a single lane exit, whereas the one in the upper right, 116th, is a full 2x2 configuration. There's some subtle differences in terms of markings. The one in the upper left has some partial concentric lane markings within the circulatory roadway, as well as hook arrows in the circulatory roadway, whereas the one in the lower right at 106 uses more MUTCD style markings and standard arrows in the circulatory roadway. So some subtle differences, but overall pretty similar. But here's the crash differences. 1/16, the full 2x2, is experiencing about 65 crashes a year over the last 3 years, whereas the one at 106 is 15 crashes a year. 106 is slightly lower volumes, about 20,000 daily vehicles versus closer to 25,000 daily vehicles at 1/16, but not enough to explain a 4 or 5-fold difference in safety performance in crashes. So this is the type of thing that we're trying to understand: is why are roundabouts that are relatively similar with similar drivers, we can't just blame it on education. Why are they performing so much differently? What are some of those root causes? That's what we're really trying to auger into as part of this study. One thing to note here is the key crash types at both these locations are improper rights, failure to yield to both lanes, and improper lefts. So at the 1/16th, the improper lefts is driving this by far. It was by far the key source of crashes. And some of the things that we've been seeing is related to lane imbalances. Some of the things is kind of the signing for lane use control and guide signing on the approaches is lacking a bit. So there's some low-hanging fruit that we can point to in terms of signing and markings that certainly could be improved. But one of the biggest elements that we're seeing is sort of these system effects. So at the one that's performing better, the 1/16th and Illinois Street, the crashes that are occurring seem to be directly related to the destination that vehicles are trying to go to. We're seeing high numbers of vehicles for the southbound right turn movement shown in red and green, that instead of being in the inside lane to make a left turn, which is the green arrows, they're actually staying in the outside lane, that red arrow, because immediately downstream, they're trying to get to a freeway on-ramp. And so by staying in the outside lane, they can get to their destination without needing to make a lane change. And so trying to make sure that we're designing the roundabouts either with spirals or enhancing some of the signing to make sure that it's clear what lane drivers need to be in is going to be important to try to get vehicles in the correct lane ahead of the roundabout and avoid some of those conflicts. Similarly, at Illinois Street, one of the key crash types seems to be drivers going to a large retail development. So they're very commonly starting in the outside lane or in the inside lane. So they're starting in the correct lane to make their left turn maneuver. Then they're either cutting across the lanes as they exit the roundabout to make that quick right turn into that retail development. Or what's frequently happening is they're just staying in the outside lane all the way around the roundabout so that when they get to their destination on that south leg, they don't have to make a lane change. So again, it's about driver perception. It's about trying to get it's trying to make sure that we're designing these instead of just focusing in with our HCS or SIDRA and looking only at the lane configurations to achieve a certain LOS, looking at how our drivers going to be navigating this. Do we have lane imbalances between these lanes that are going to be impacting operations? And how can we get it so that the drivers are getting to their destination without needing to make a lot of weaving maneuvers and lane changes that might impact how drivers are perceiving how to navigate it. So kind of just a quick overview of what we've been looking at so far. Hope to be able to share a lot more on that pooled fund study by the end of next year, and specifically some of the countermeasures. But some other updates of other ongoing research. We've got an update to NCHRP 672 that's currently ongoing. That report is now 10 years old. It was published in 2010. And so there's been a lot of updates and a lot of research that have happened in that time that'll be synthesized into that new document, including some of the stuff that Zach presented on, but then also other topics like updates for guidance for design vehicles, tractor trailers, and oversized overweight vehicles, and those types of topics. Also a quick note that FHWA did recently release a informational primer on turbo roundabouts. For those of you that may not be aware, it's available at the link that's at the bottom of the screen on their roundabout resources page. Turbos are definitely an evolving practice in the US and something that is going to be of interest to some folks. And so that gives some nice introductory information for those that are interested in exploring that topic further. I'll note that FHWA is interested in some of the turbo aspects as potential countermeasures for the topic that we just talked about with the exit crashes. But just note that when you get into the 2x2 configuration of roundabouts, that if you're trying to convert to a turbo, because of all the spirals that are needed, you may be needing 3 circulating lanes all the way around the roundabout for a turbo compared to your 2 lanes in a traditional multi-lane modern roundabout. So the turbo has the potential to help address some of those conflicts that we just talked about, but in some locations it may require a bigger footprint and may not be that magic silver bullet for all locations. So anyway, with that, we will wrap it on up and go on to the next presenter.
All right, thanks guys. And if anybody has any questions for our presenters, please put them into the Q&A section of the chat and I can read those off for us. I saw we had one comment that I've now just lost, but I think it was from Don Bennett, who mentioned that he said he can see where designing a multi-lane roundabout can be problematic in high growth areas where OD patterns are changing. So feel free to get your questions sent to the chat and I can get those read. And I'm going to go ahead and introduce our second speaker, which is going to be Dr. Joe Hummer. All right, Joe is the State Traffic Management Engineer with the North Carolina DOT Mobility and Safety Division. He specializes in alternative intersection and interchange designs. Joe began researching the designs in 1990, has published numerous articles about them, and has invented several new designs. His 2-part series in the IT Journal in 1998 helped create momentum in this area. He has a BS and MS in civil engineering from Michigan State University and a PhD in civil engineering from Purdue University. And Joe is also currently the Vice President of North Carolina section of ITE. So let's welcome Joe. He's going to be talking about the double contraflow intersection. Take it away, Joe.
Thank you, Kevin. I'm going to try to share my screen here and pop up some slides. How about that? Is that sharing?
Yep.
Fantastic. So it's a pleasure to be here with you today. I do appreciate the opportunity to lob in a new design. Kind of claim credit for this one as one of the new inventions. We'll see how it goes. And appreciate the chance to kind of try it out here among this group and see whether you like it or not. The double contraflow intersection. And what I've got in mind is what can we do about places like this? This is not in North Carolina, but we do have sort of some intersections like this in North Carolina. This is a 8-lane arterial meets a 6-lane arterial. Currently has a median U-turn design, but in the peak hours, at least non-COVID peak hours, This thing is badly over capacity. As you probably know, a median U-turn delivers decent capacity, better than conventional. Of course, anything beats conventional. But a median U-turn eventually gives up to, it just doesn't have that much more capacity because all the vehicles come back through the intersection a second time, all the left turns. So what can we do here at this kind of place? Two big busy arterials meeting each other. Well, we could create a grade separation, but that's going to be very costly, very impactful. It'll solve the congestion problem, probably, but it will create other problems instead. CFI is probably the current champion in this niche of two big arterials meeting. And a CFI does provide a lot of extra capacity, but a CFI has a couple of well-known sort of Achilles heels, and those are pedestrians and driveways. So in a place like I showed you there actually were decent pedestrian demands to get across 8-lane and 6-lane arterials. And if you saw the picture, there was a decent number of driveways on the approaches, and CFI would be tough on those as well. So we move on. We think about maybe a quadrant roadway intersection, a connector road, and there's a few of those out there. And of course, so we have a new Federal Highway Administration guidebook on QRI, but the quadrant has the difficulty of getting right of way for the connector road. And in a developed area like the one I showed you, that's going to be pretty impractical. So, and then the median U-turn, like I said, a lot of good features of a median U-turn, but not a very high capacity as it turns out. So we're kind of stuck at a place like that with oftentimes still not a lot of good options really to knock it out of the park. So what can we do? Well, we can do this thing. The new invention that I'm bringing here today, double contraflow intersection. Actually, I tossed this in at a presentation, I think last year's annual meeting, just one slide, just a little teaser. But since then, I've had a chance to work on it more and develop some results, some quantitative results, comparing this double contraflow DCI to the other designs in this niche. Let's see how it does. The idea behind the double contraflow is to move the left turning vehicles so that they never cross each other. So I tried to show that in red and green on this slide. The northbound left turn in red goes to the left of the southbound left turn, which is in green. So those left turning vehicles never cross each other, never conflict with each other, and there's the extra capacity boost. It's similar to CFI in that regard, where the left turn vehicles never cross each other. And in fact, at the main intersection, it operates very much like a CFI, in that the left turning vehicles move at the same time as the throughs. Instead of a CFI though, in the double contraflow, the left turning vehicles cross at the main intersection, head downstream a little ways, and then make a U-turn at a bulb out, and then come back to the main intersection and make a right turn. Two-phase signals, got 5 of them, one main one in the middle of the intersection, and then 4 secondary signals. But the U-turn signals, the secondary signals, are easy to coordinate with the main signal, and really drivers, through drivers, right turning drivers, should only have to stop once, if at all. And the knock on contraflow through the years, when it's been used at, especially at interchanges, is that there's a potential for a wrong way movement for especially left turning drivers coming out from the side street onto the main street. That those contraflow lanes offer that driver a multiple choice of 4 different paths. And that's not a good thing, especially for an unfamiliar driver at 3 a.m. But this design at the main intersection, there are no left turns. So I think that the chance for a wrong way movement into or out of a contraflow lane is pretty minimal. And that's one reason I'm attracted to this. I should note along those lines, there's not really a single contraflow intersection in my mind anyway. I don't think we can do a partial of this thing, because then we would introduce the chance for a wrong way movement. I think that potential is too high, my judgment. But with all 4 left turns being made contraflow, the main intersection does not have that potential, I think. So is there a niche? In North Carolina and other states, could we see a DCI double contraflow compete with a CFI? I'm showing a picture of the one and only CFI we have in this state right now, and that's suggesting DCI would have been a better design there. But at the next generation of these kind of places, could DCI compete? Will it have less impact than a quadrant or a grade separated intersection? Almost certainly. Will it have higher capacity than median U-turn? Almost certainly. And will it be better for pedestrians and driveways than a CFI? Yeah, pretty sure of that too. So I think at first glance, qualitatively anyway, there might be a spot for the DCI. And in the next few slides, I'll kind of go into that case quantitatively. As far as capacity results, just running a series of critical lane analyses on a wide range of demands, the results came up like this. Compared to a conventional design, median U-turn is 9% better on average. CFI is 11% better on average, and DCI is 15% better on average. It's not hard to see why. The little diagrams at the bottom of the slide should convince you pretty quickly why that is. The DCI at the crossover, which is the capacity bottleneck, at the crossover, the DCI has 3 vehicle streams that move, conflict with each other. The CFI has 4, and the median U-turn has 4. So it doesn't take a genius to see, well, 3 is less than 4, and therefore the DCI probably has a good chance to be providing higher capacity than those other 2 designs. Run out the numbers for your particular case. It depends on the combinations, how many rights, how many lefts, which lefts, all that kind of stuff. But I think in general, you can see the case there for DCI being a capacity solution. With my colleague Amir Molan at Cal Poly University, we ran a big VISSIM experiment across a huge wide range of demands, really 4 categories of demands, what we call very high turning, moderate turning, and low turning demands. We compared conventional to CFI to DCI. He's about to finish the runs for median U-turn. We'll have those soon, but I don't think they'll change the bottom line here, which is that the DCI, as you would expect, based on the capacity, was generally superior. Pretty close to the CFI, but remember, these are travel times that also take into account the fact that DCI left-turning vehicles travel longer distances than in a CFI. So even once we take that into account, we see that the DCI usually outperforming the CFI, and of course, beating the conventional again is no big deal. Everything does. One other factor in favor of the DCI is better progression than the CFI. CFI is good, but DCI, as far as timing those signals and getting everybody through with 0 or 1 stops, is easier at the DCI. So overall, bottom line, you can see there, DCI a little bit better than the CFI, not statistically significantly different, 170 versus 179, but compared to the conventional at 234 seconds per vehicle average, quite substantial difference. We ran the NCHRP 7-25 method, the so-called 20 flags method, on these competitors to look at pedestrian and bicycle movements. And let's take a look at those here in this slide. For pedestrians, you might remember that there's 52 potential flags at a 4 approach intersection. The DCI, not quite as good as median U-turn. Median U-turn only had 8 flags, DCI had 12, but DCI better than conventional, which had 16 flags, and better than CFI, which had 16 flags. DCI gives pedestrians a better deal based on this methodology. Turning over to bicycles, right side of the slide, DCI, the same as median U-turn, not quite as good as CFI, which only had 52 flags as opposed to DCI 56, but all of that better than a conventional design, which requires bicycles to be quite, how do you say, gymnastic inclined to get across a big intersection like that. So a DCI middling for bicycle, roughly the same as median U-turn, but better than conventional. As far as safety goes, of course, we really don't know until we actually build one and look at some crash rates. As we saw even with the previous presentation, multi-lane roundabouts, we're still working through the safety impacts of multi-lane roundabouts 20 years after we built the first one. So this is an evolving part of the science, but we do what we can. One of the things we can do is take those VISSIM results, process them through that program's SAM, and look at how many conflicts each of the designs cause. And the results are in this slide. Bottom line, again, overall, DCI slightly better than CFI and much better than conventional. It just doesn't cause that many conflicts, which hopefully would translate down the line to fewer crashes. Somewhat more lane change conflicts because of drivers making those U-turns and getting into the left turn lane and such, but fewer rear end conflicts, and that's mostly because of the extra capacity. Other things we can infer about safety at this point of the DCI, we can run that new model that ITRI came up with that you might remember, the so-called movement-based safety prediction model that they presented last year. And when we do that, we see that DCI comes up about the same as conventional, a few more crashes than the CFI, and actually many more crashes than the median U-turn. We've known for many years, median U-turn is really excellent for safety and excellent for pedestrians. That's what I'm seeing here. And if those are the driving forces at your intersection, you should probably stick with the median U-turn, but it just doesn't give you that much capacity, right? DCI, more distance traveled, which would lead to a few more, let's say, run off the road crashes, more fixed objects, more unusual maneuvers, but also shorter queues, so that fewer rear end crashes in the end, we would guess. Let's pick this topic for a moment, that the behavior of that left turning driver, if they can find the contraflow lane, which we're going to need great signing and marking and cooperation from our friends at Google and Waze and et cetera, for that to happen. But if they find the contraflow lane, once they're in the contraflow lane, would the drivers be nervous? And then once they get to the signal in the contraflow lane, will they know enough to go straight? That's I think, going to be really critical, that driver behavior piece. We're going to need the right signs, markings, signals, and yes, enforcement to get drivers in that contraflow lane at the main intersection to just go straight ahead. Follow the cars in front of them would be a good notion. Hopefully we can do that in a future era of connected and automated vehicles. That'll get much easier. Don't have to worry about the silly drivers anymore. But until then, we're going to need good traffic control devices to make sure that takes place. A few words about driveways, because remember, that was one of the Achilles heel of CFI. And you can see by this measure, which is the number of movements needed to get into and out of, actually make left turns into and out of driveways on the approach or on the departure side of an intersection. The CFI is really pretty bad. No sugarcoating it there. Driveways at a CFI are really tough. Median U-turn, not great. DCI actually about the same as median U-turn, maybe a little bit better in this regard. And of course, conventional is the best of all as far as the aspect of driveway service. Let's remember though, the extra delay that a conventional intersection would bring, and the fact that if you chase some of these paths, there's a lot of longer distances with the conventional and with the CFI than there would be with median U-turn or DCI. So the numbers on the slide here, I think, help a little bit and clarify that. I think when you also take into account the delay and the distances traveled, the DCI actually comes closer to the conventional, but it's probably still not better. But I think you can make the case the DCI will be better than the CFI for sure in the dimension of driveway impacts. As far as right-of-way goes, one of the things to realize here is that DCI is going to need a larger bulb out, and that's because the U-turning vehicle starts further to the left than a median U-turn. Try to quantify that in these numbers. DCI is still a little bit less right-of-way than the CFI, which of course requires a big chunk of right-of-way over to the left side of the approach to get those ramps in place. We didn't run the numbers for median U-turn yet. It's certainly less than a DCI, probably more than a conventional, but less than a DCI. Probably on this scale comes in somewhere around 100,000 square feet would be my guess. So DCI better than CFI in this measure as well. So to wrap up, thanks for hearing me out on a new intersection. I think there's a niche here, but we've got a lot more to do to verify that. I think it's pretty clear it's going to deliver higher capacity. Really no real question about that. And then with that should come better travel times. And I'm comparing here to a CFI. And the pedestrian impacts will be better. The driveway impacts will be better. The right-of-way impacts will be better. We don't know about safety. We still really don't know about the safety of the CFI either. Have to really get some in the ground and measure it out. As far as I can tell at this early stage, the DCI doesn't look too unsafe. The one negative impact, as far as I could tell, that I measured was bicycle impact, where the CFI looks to be a superior design for bicycles. So please consider this one. I think there's a niche there, again, at these big whopper intersections where there's just not a lot of other choices. Don't have a lot of other good ideas out there for such places. We need a lot more research, driving simulator work for sure, to see if the drivers will do what we ask them to do. We need to include these new designs, a lot of new designs, but this one in particular in CapEx and VJust, so people can run the numbers out. We're going to need good public relations. We're of course going to need some crash data after we get one built. I think there's some potential for contraflow lanes in other configurations. Of course, I've kicked the tires on interchanges with contraflow lanes over the last few years, but maybe even some other intersection designs. I don't think we've exhausted all the possibilities yet. Again, because the capacity boost is just so wonderful for contraflow lanes, basically free capacity in the same space just by rearranging where the left turn lanes are. And then I mentioned the automated vehicles before. So I do appreciate the time and the chance to spot off at intersections a little bit. That's my grandson fixing traffic in his world. Let's go fix traffic in our world. We've got a lot of interesting, exciting sites out there. Let's get back to it and let's go fix some traffic. And again, thanks to co-author Amir Milan, who's doing good work out in California. Great. Thanks, Kevin. Back to you.
Hey, Joe, we got a couple of questions in the chat, and you kind of touched on this when you talked a little bit about left turn driver behavior. We had a few questions about just the potential for illegal left turns at the main intersection, and just that, there wouldn't be much stopping folks from trying to just wait for a gap and make that left turn like they would normally expect to do. Can you speak to that a little bit?
Yeah, there wouldn't be much stopping, folks. I'm, of course, a native of Michigan, where we've got a lot of the median U-turn, and we don't have a problem with drivers making the illegal turn with a similar temptation, because there's a lot of peer pressure. If in Michigan, if you pull up and try to make an illegal left turn out of that through lane, your fellow drivers will let you know you're not doing right. Various gestures, various maybe these days they'll flash some firearms, whatever it takes there. So let's not discount the driver peer pressure, right? Enforcement certainly will help. Public relations will certainly help. And also good design. I think we're going to need paint on the road to show that those drivers in that lane just need to go straight ahead by whatever means we can paint those lines there, signs, signals, all those things. But let's not discount the peer pressure that's very obvious to me that works up in Michigan.
Thanks. Good stuff.
Okay, I'm going to stop sharing. Thank you, Kevin.
All right. Thanks, Joe. All right. So I'm going to introduce our last couple speakers that are going to be talking about the dynamic left turn intersection that was recently installed in Cary. So starting with Dr. Jeremy Chapman. Jeremy is a graduate of Marquette University, University of Illinois, and University of Wisconsin. And he's worked in the traffic safety and transportation field as a consultant, expert witness, researcher, and university faculty member for the past 20 plus years. He is certified as a professional traffic operations engineer and a road safety professional. He's also the national chair for the ITE Ethics Standing Committee and member of the ITE National Coordinating Council. As a consulting engineer, Dr. Chapman focuses on sustainable safety and human factors. He joined Ramey, Kemp and Associates in late 2019 after him and his wife moved their family to Asheville, North Carolina, as she accepted a faculty position at UNC Asheville. And Jeremy's going to be speaking today with Joe Milazzo. Joe directs the regional business community's leadership and advocacy efforts on transportation issues, policy, and strategy. His primary role is to bring the business community together, leverage their strength, and accelerate success on key priorities for our growing region. Joe holds master's degrees in both business management and civil engineering from NC State and a bachelor's degree in civil engineering from Penn State. He has been a licensed professional engineer in North Carolina for more than 20 years and a registered lobbyist in North Carolina for more than 15 years. He has been with RTA since 2002. So let's welcome Jeremy and Joe. I will turn it over to you guys.
Sounds good, and I'll lead us off. I'll go share my screen right now. Let me pull that up. Just a moment. I got it here. And just 1 second here. See if that works. And is that visible, Kevin? Can you see that?
Yep, you're good to go.
Okay, that sounds great. Put this over here. Well, welcome everyone to the final presentation for the Evolving Intersections track this morning. This is development and evaluation of the dynamic left turn on your agenda. You see on the screen, America's first dynamic left turn, pilot status, 9 months on. You've heard from both Joe, or the introduction, very kind, for myself and my colleague Jeremy. A couple quick thank yous, Sarah, Sarabia and Kevin for the planning and moderation. I want to thank you guys. I do want to thank the NC section and today's sponsors for making this event a reality. Every Diamond sponsor is also an RTA member, so we appreciate your membership in RTA too. And really want to thank the presenters this morning already, Zach and Justin and Jim and Joe, for your presentations on the multi-lane roundabouts and the double contraflow. I think this presentation that Jeremy and I are going to do is really a natural complement to that. Also, a huge thank you to NCDOT and the town of Cary for the partnership. They have done the installation, funding, and monitoring. And our last presenter, Joe Hummer, has actually led much of the effort for the department on this. So I want to certainly thank him as a very long-time colleague and friend. I also want to thank our RTA member firm VHB. They've done the before and provisional after study that's still ongoing. In terms of level setting for the presentation this morning, my co-presenter, Dr. Chapman with Ramey Kemp, has provided some outstanding and ongoing guidance on human factors. He'll be speaking to that about halfway through. I'm going to talk briefly about the purpose of the DLTI, the development of it, and the evolution over time. And again, it's the first one. So let's get right to it. So if you look at this, I'll go to the next slide. Let's make that right. Dynamic left turn intersection. Before I even read that, and you kind of get where I'm going, but let's even back up a step. When you add a second left turn lane at almost any arterial intersection in this state or across the country, we typically make that signal protected only. And that has several impacts, and some are very positive and some have some challenges with them. The positive ones are numerous. One, it's more efficient during that phase. There's no conflicts. You're providing clear direction to the motorist. You're getting effective platooning. You can minimize the duration of the phase as a result. A lot of very positive impacts of making that protected. Protected only left turn has several negative impacts, of course, and we know those. You kind of get an allusion to that by looking at that intersection. That happens to be an intersection in Cary. It's not the one that the DLTI is at, but just happens to be one. Protect only left turn has several negative impacts. One, you have to display a dedicated phase in order for even one vehicle to turn. And of course, everyone else has to wait while you display that for even one vehicle. And what is a result of that? Your cycle length goes up, your delays go up, your travel times go up, voluntary compliance can suffer. And of course, maintenance is also an issue because you can be showing phases to no one, depending on how that's going too. So that's the trade-off. So good things about protected left turns, it's a standard practice, but there's some challenges. So we're kind of getting to the why. So the dynamic left turn intersection, we'll get to more what this is in a second, but the goal of this is to create a permitted phase opportunity for movements with 2 left turn lanes at signalized intersections. That's the purpose of the question. That's the reason why we're looking at it. And you might say that sounds familiar because if you have a dual left flashing yellow arrow, which wasn't discussed this morning, but we've seen it before, and there are several around here, including actually in Cary. In fact, has several of them, but there are others. The goal for both of those is identical, to create a permitted phase opportunity for movements with 2 left turn lanes at signalized intersections. So that's just another way of attacking a particular problem or dealing with the trade-off more specifically. So what I wanted to do today or this morning is first start speaking about the dual left flashing yellow arrow, the use case there, and then we'll talk about the dynamic left turn. And again, credit to the department, they coined that phrase for this. You might also think of this as a dual left flashing yellow arrow. That's what's called, or excuse me, variable left turn. So here we go. Dual left flashing yellow arrow. What is the use case for that? Well, you'd have adequate sight distance for both left turn lanes. You need to have that if you're going to flash the yellow arrow and allow both left turn lanes to execute their turn during that phase. You also should have no significant concerns about adjacent turning vehicles encroaching on each other while executing the permitted left turn or the dual left turn there. So if you think about the swept paths or the vehicle paths, you'd want to feel confident as the engineer that that's not an issue. And if both of those things are prevalent or present, then a dual left flashing yellow arrow it could be a very appropriate solution. Another thing to mention is time of day can be a part of that. So for example, while it doesn't have to be this way, you could certainly do it while your peak period, both left turn lanes are open, protected only, and then off peak, both left turn lanes are open, and you could go add a permitted phase, could protected permitted, could do permitted only, of course. But so those would be options there. You could also reverse it depending on if the focus is more about cross product versus speed. But again, that's the main point, is to talk about for a dual left flashing yellow arrow, that time of day is appropriate or can be done. So then what is the dynamic left turn? We're going to get to more of that in a second, but the dynamic left turn, which is really varying the number of lanes available by time of day. The use case is similar, but not exactly the same. So in this case, it's adequate sight distance for the leftmost left turn lane and marginal, perhaps, for the rightmost left turn lane. And you can see, I'm not sure if you can see my arrow here, but on the leftmost left turn lane, obviously that's closer to the left. It's a shorter travel path. So from a crash vulnerability standpoint, the left one is easier. Again, it's effectively a positive offset left turn. The rightmost left turn lane might be more marginal. Another reason you might look at a dynamic left turn would be if you have concerns about adjacent turning vehicles encroaching on each other's paths while you do it. And so you might want to minimize that. So talk about what this is. So what is the dynamic left turn? To implement it, you simply close the rightmost or the outer, however you want to call that. You close that left turn lane during the periods of day when you want to have the flashing yellow arrow phase available. You can see that here. This is a simulation or an image of a simulation created by the department. I think it's very well done. And you can see the red X displayed electronically over the rightmost left turn lane. The leftmost left turn lane, it's a static sign. It could be dynamic as well, just for visibility, but the first installation has been static. And of course, you see a 4-section head posted there. I'll switch to the next slide here. So how does the variation go by time of day? And again, credit to NCDOT for these graphics. Similar to the dual left flashing yellow arrow. During peak periods, both left turn lanes are open, protected on the operation. In fact, that's identical to what you would typically do for a dual left flashing yellow arrow. And that makes sense. If you think about the reason we install dual left turn lanes at any intersection is you're dealing with a capacity issue, you're dealing with a heavy volume or heavy phase volume during the peak period. You want access to both of those left turn lanes during the peak period. And of course, as I mentioned earlier, protected operation can make that more efficient as well. So whether it's a standard intersection, a dual left flashing yellow arrow, or in this case, a dynamic left turn, the peak period operation is typically the same, where you'll have 2 left turn lanes and they're both open and they're both protected. What's different here on the dynamic, the time of day variation is like this. In the off peak, as I mentioned earlier, the inner leftmost lane is open, and you can see that on the left side, or excuse me, on the right side of the graphic, while the outer rightmost lane remains closed to traffic. And so that's how that's working. So what in essence you're doing is you're creating a positive offset left turn dynamically during periods of the day when you simply don't need both left turn lanes. That's the thinking behind it. Here's a couple more graphics, and the one on the right shows the actual installation in Cary. Again, I've mentioned the design. It's a single 4-section left turn head. Of course, your flashing yellow arrow is part of that. That's a standard device. It's mounted above the 2 left turn lanes. Lane use control signals both at the intersection itself. You see that on the span wire. And then if you look on the graphic, you see an advanced span wire, the X, and which is dynamic, of course, and the static left turn only sign. The department did add an additional sign saying lane closed on red X to help emphasize what the X meant as well. Move this down. This graphic here is just another one. It again shows a graphic you've seen earlier, but it shows the comparison, driver's eye view, simulation type, dual left on the, or therefore peak period on the left, on the right side, the off peak. One thing I do want to mention, I showed the fact that the first one in the country is in Cary. The department went through a process to determine which one they were going to pick. They had a number of criteria. One, you had to have 2 left turn lanes. That had to be a part of the criteria. They wanted criteria or intersections when they were thinking about a potential location where there was sufficient left turn demand, such that both left turn lanes were needed during some peak periods, but not so high that you needed dual lefts all day. If you did, this is probably not the best of all possible solutions. Another thing you wanted here is a sight distance piece of it. Again, sufficient sight distance for left turning drivers, for permissive left turns from either lane, since it was the first one around. As this evolves, as this continues to evolve, the best locations for this, again, are going to be places where the rightmost lane is more marginal. If both left turn lanes are good sight distance and there's not real issue of swept path under permitted phase, then your dual left flashing yellow arrow is a superior design over this, and you don't need to go through this process. Other criteria the department used was having a city or town with engineers and leaders receptive to innovative solutions, in this case, dynamic left turn. And there have been actually several that were interested in this, and the one that worked in terms of a location meeting these criteria within the triangle market, signal system was ready, was in Cary, and this particular location is at the corner of Tryon Road and Cary Parkway near the Colonial Baptist Church, about a mile from that. So what I'm going to do is turn this over to Dr. Chapman. He's going to offer some thoughts about the human factors elements, and I'm going to talk a little bit more about the performance, and then we'll take questions as well.
Thank you, Joe. So I came into this actually after the deployment first was installed, just to kind of give an initial human factors review and also to look at kind of the initial data that had come out of basically just its first months of operation. And we discussed a lot of different things. And a couple of the critical things that we started to find with some video recording and other things of operation was, while there was a fairly high compliance rate, there still is the occasional, we'll call them a sneaker, or somebody who decides that they don't want to wait behind the queue and they're going to jump over to that right-hand turn lane to get around the queue, even though that lane is blocked off. Obviously, there's nothing to prohibit them from doing so. It just creates possibly obviously a conflict situation if drivers are in the left-hand lane, all assuming that there won't be anybody in the right-hand lane when they make that turn. So the issue, I think it was actually shown in maybe both Joe Hummer's and also the Roundabouts presentation that we faced as well, is that after you make that left turn, there is a shopping center on the right-hand side that drivers may or may not want to access. So if they're in the left-hand lane, are they going to make that as a soft left rather than staying in their lane, going from inner lane to inner lane? Or are they going to drift across to the outer lane and making that turn? Also possibly an issue for turning radii for trucks. So those were all things that were considered and looked at. And one of the factors, or one of the solutions that we came up with, at least as a temporary idea, instead of using the typical skip dash to designate the center between two turning lanes, we decided to make it a full solid line. I don't know, Joe, is that in?
Yeah.
That's in the next slide. You can see that if you want to advance. So you can see where we repainted from the skip dash to a solid white through that. And I think I'd have to go back and double check, but I think we actually received or achieved slightly higher compliance yet, just for drivers seeing that a solid line. That little human factors trick actually had a pretty good response to it as well. But mostly, some of the other issues we looked at were what the right configurations of signals would be. Do we want to think about having a signal head for each lane rather than a shared one across? And part of this was trying to do this as, Joe didn't mention this, I don't think, earlier, but one of the other critical factors was to accomplish this without having to do anything experimental per the METCD. So could we do all of this with technology that is straight out of the manual and applied per the manual? And between the federal and the North Carolina METCDs, that was achievable with these configurations. Another issue we looked at, and I think you can make it out a little bit here, is we did worry a little bit about drivers that missed the entrance to the double turn lane because it's back far enough, sneaking across and then trying to make that left turn from the right-hand lane, basically moving over from the through lane into it late and kind of getting stuck there. And we looked at a few different ideas for how to emphasize that separation line, and we decided, I think, to go ahead with a wider or a darker, or pretty much a wider white stripe than a normal, just 4 or 6 inch, but actually making it a much heavier white line separating the through and the right hand left turn line or lane. So those are kind of some of the factors that we looked at primarily from the human factors standpoint. And obviously we will keep evaluating the human factors elements as this matures and we see new behavior patterns. Thanks, Joe.
Yep, absolutely. Thank you. And again, it's an evolving intersection as we go. That sign was added later. As Dr. Chapman mentioned, the line through the street was added, or through the intersection was added. I don't believe the wider line between the through and the lefts has been added yet, but to his point, that's exactly where we came up with in terms of the next potential countermeasure or potential modification of it. A couple other things, places where you might not use this. 3 or more opposing through lanes, you probably wouldn't use this or even dual flashing for that point. And if you can't have adequate sight distance for 1 or more left turn lanes throughout the day, then you probably wouldn't use this or dual flashing for that standpoint. A little more about the pilot. It has been open for more than 9 months, back since February of this year, a little over 9 months now. Some drivers are saving more than 2 minutes of travel time per cycle. Again, VHB has done some analysis very good for that, and they're finding some of that. In fact, their analysis showed that in terms of the typical assumed value of time and estimated time savings, that the install cost has been paid for itself in that regard, actually paid for itself back in July. So that's a positive sign for this. It is a low cost improvement. Dr. Chapman mentioned some of the compliance. Prior to the pilot, most of the turning vehicles were using that rightmost left turn lane, whether that was to go into the shopping center, whether that was to hit the US 1 freeway, which is just further down the road here. Now the pilot's been active, it's about 85%, my understanding maybe a little higher than now, are using the left turn lane properly when there's only one lane. Of course, when both lanes are open during rush hour, both lanes are absolutely fine. But that's a significant change. And as Jeremy mentioned a little bit ago, there is a heavy demand on the right side just after the dynamic turn. In terms of enforcement, I'll simply mention there have been some citations that have been issued for using the closed lane during off-peak periods. But I would say the number of those has been limited based on my understanding and conversations with the town of Cary engineers earlier this month. Some lessons learned for this one. Again, it's the first in the country. And as Jeremy mentioned, absolutely one of the elements of it when we first talked about the concept of this with the representative from Federal Highway, and they even offered suggestions to make sure it was compliant, it was not experimental, and that's what you've seen the result of. Again, clearly conveying the expected benefit for the public. Why can't I use the rightmost lane is one of the big questions that came up. And the answer, of course, is the sight distance issue. That's the reason why. Explain the use case for practitioners. We're trying to do that this morning. Adding the sign explaining the X. Well, on the one hand, we all know that red X means the same whether you're on a bridge with tidal flows over a river in Philadelphia or the Chesapeake, for example, or at your local bank, red X, or at Edwards Mill Road, it means the same. The reality is in a new context, it can still be unexpected and the sign can help. The striping was added, we mentioned that, and then Jeremy also mentioned the concerns about traps in the left turn lane. Regarding cost, it is low cost, probably between 20 and 35,000. I think this initial install is a little closer to the higher amount. That includes, again, your advanced span wire and the multiple lane control signals. To be clear, if you can do a dual flashing yellow arrow, if you can do that from a sight distance standpoint and operation standpoint, that's superior because you don't have any questions about which lanes you're using, and it's also a little lower cost since you don't have advanced signals. This is for the use case as I mentioned previously, but either option would typically make a very competitive spot mobility project submittal with the department. Next steps. Mobility and Safety does consider this a successful, still an ongoing pilot. I think they're even open to removing the pilot name now it's been over 9 months. There's still a final comparative analysis that's still held in abeyance a little bit due to the pandemic. Because it was installed prior to pandemic, we don't have comparative one-to-one volumes. The department is sharing information with this organization here, with TRB. Other states are asking about it. It is eligible for implementation in other locations now, so that is positive. So there's a final view of it. Again, that's the location in Cary. It's been our pleasure to offer that perspective on it. And here's contact information for Dr. Chapman and for myself. And I will leave the screen share up and happy to answer questions during the time left if there is some. Looks like there is. It's about 11:48.
Yeah, we got a few questions in the chat, and one of them related to the how much discussion was put into the signal head configuration. You know, there was a question about whether there was consideration done to use one left turn lane, one left turn signal head as opposed to two signal heads. And Jeremy, I know you touched on that relative to the MUTCD considerations. Anything to add to that?
I can add initial, then Jeremy can add. So actually, when we first started this, we actually did look at two. That's actually where this began, looking at one signal head for each lane, because that's standard practice. And we were actually looking at some other locations where you had, you know, I'd say red X's or different numbers of lanes usage for tidal flows, and looking at, there's a location in Kentucky, I think it's since been uninstalled. There's one in Utah where signal heads were dark during periods where they weren't being used and so on. We checked with Federal Highway, that actually the contact that NCDOT gave us, and they said, you can't do that. You got to have it active. And so we couldn't figure out a way to do it. And they said, well, what you could do is just install this over the lane line, and then that would be MUTCD compliant. So actually our initial thing was to do that. But our contact with Federal Highway said, just install 4-section over the lane line and it would be. So that's where that started from. Jeremy, you may have other thoughts to add.
Covers it. And then the other issue too, or I think the solution actually that works out well, is that red X, because it's so universally known that, and it's actually more visible from all the way back at the start of the storage lanes, that it seems to, I think it seems to solve its or accomplish the task fairly well. And maybe more visible than the signal head would have been anyway.
That's a great question, though. That's a very good question. Yep.
All right. I don't see any other questions from the group, so do appreciate your time, Joe and Jeremy. Thanks for the great presentation. Appreciate all of everybody's time. Especially want to thank our speakers. Let everybody know that I guess we're taking a lunch break, but should be back at 1 o'clock for 2 more sessions, one featuring multimodal projects in the Triangle, and then one discussing NCDOT's new project delivery process. So before we go, I want to give one more shout out to our session sponsor, Stantec. Thanks, Stantec, for your support of Nixite. And thank you to you all for your attendance. Everybody have a good afternoon.